Okay, everybody, welcome to our TAPAS training event. Today, we invite Chu Qiangkong to give us a talk. Dr. Chu Qiangkong is currently an audio and music research scientist in ByteDance. Previously, he obtained his doctoral degree from University of Surrey in 2019. His research topics include audio tagging, sound event detection, source separation of real-world sounds, general audio processing, and music signal processing. He is interested in sound understanding and audio processing with artificial intelligence. Chu Qiang, please go ahead with your talk, please.
Yeah, thanks for the invitation from Zhao. I'm Chu Qiangkong. I'm very glad to share what we have in the company of ByteDance. So just a brief introduction of myself. I have been graduated from University of Surrey in 2020, and I have been working as a research scientist in ByteDance for 2 years. My research interest includes audio tagging and every understanding of sound. So today I'm going to talk about AI for sound, a large-scale audio tagging system with deep neural networks. And also I hope my experience can be helpful for those PhD students who want to look for a job. And I will briefly introduce the difference between the industry and the academia during my talk. First, so let me introduce 5 basic scenes of human. Humans have 5 senses, including sight, hearing, smell, taste, and touch. For sight, we have computer vision, and for hearing, we have computer audition. So my research is mainly focusing on hearing, so it's about computer audition. So the reason why we want to do hearing in the company is that we are the company building TikTok, and the music is a very important part of the products. So we want to design some products that can be helpful for humans, can be helpful for teenagers, and also everybody to play sound and play music. So this is the reason why the company are hiring people who are researching the sound. And for computer audition, this is a general field of study algorithms and systems in audio understanding by machine. And computer audition is to solve a wide range of problems, including tagging, classification, detection, localization, and separation and generation. And the final goal is to let the computer to hear and understand audio contents as humans do. Here are some relations between computer audition and computer vision. So we all know computer audition is a very well-researched area, and there are more people doing this area. So we can bridge some connections between computer vision and computer audition. For audio tagging on the left, this task is very similar to image classification, where we want to predict the text on a spectrogram. And for image classification, we want to predict the tag of an image. The second task is called sound event detection. For sound event detection, we want to detect the precise onset and offset times of sound events. Similarly, for image localization, we want to localize where the people are brushing their teeth and do whatever things they are doing. The third task is called source separation. For source separation, we want to separate different sources from a mixture. And this is very similar to image segmentation, where we want to segment each pixel from an image. There are also other applications, including speech synthesis. Speech synthesis is close to image generation. Well, for the synthesis task, this is a very important part in the company because we want to build speech synthesis functions for the mobiles, for almost every applications which are interacted with humans. So we have almost tens of people who are researching speech synthesis. and there are several groups doing this kind of research. We also want to control the emotions and also the text of the synthesis. So this can be slightly different from the research, where in the industry, people are mainly focusing on the hearing quality or the perceptual quality of the speech synthesis, the speech. The last one is called audio three-dimensional reconstruction. This is very similar to image three-dimensional reconstruction, where we want to play the sound in a space, and we can hear the three-dimensional sounds from different directions. So let's see the applications of computer audition. The first one is called audio-based information retrieval. For many applications, for example, the mobiles you are playing or the internet you are using, so we want to retrieve audios based on the content. And this can be helpful if we want to retrieve some audio we are interested in. For example, if I'm interested in watching movies including gunshots, so I can input a gunshot, and the result will return the segments containing gunshots. The second task is called music tagging. This is a very basic application in the industry because we want to do recommendation systems. Before the recommendation systems, we need to build music tagging systems to extract the tags of music or the embeddings of music. By this way, we can build the music tagging systems and use music tagging systems for the recommendation systems. The third one is called transportation assistant. Imagine you are on a street and there are many cars. So we want to detect which car is alarming. So if the car is alarming in a rear, which it shouldn't be an alarm, so we can detect that. The fourth one is called surveillance. So this is more related with security. So if there is a scream or a fire alarm, so we can use our systems to detect the fire alarms automatically. The next one is related with industry and military. So we have many factories, but we can't set a lot of people to listen to the sounds that are not working properly. So if we have an automatic sound event detection system to detect the abnormal machines, then we can save a lot of money. The final one is related with home and health. So everyone has a baby or a grandmother. So if our grandpa is falling down, we can use our detection systems to let us know that your grandpa is falling down. So this is very important if we are at work or there is nobody at home. We can also use our systems to detect the snoring of people or detect some heart sound or whatever sound that's related with health. So those are the applications related with the industry. And I believe there are also interests that the universities has already researched. So in the next slide, I will introduce the hearing mechanisms of human. Sound is a vibration that typically propagates as an audio wave of pressure through a transmission medium such as gas, liquid, or solid. The infrasound are sounds lower than 20 hertz, and ultrasound are sounds higher than 20,000 hertz. Audio is recorded sound in digital format. Human has a hearing range between 20 and 20,000 hertz. It's very interesting to see that dogs have a hearing range that's wider than human. Usually, the vocal sound has an approximate range between 110,000 hertz, and music has an approximate range between 50 and 20,000 hertz. On the figure to the right, we can see different ranges of different sounds. And for vocals, it is in the middle, and the frequency is very very narrow. And for orchestra, the volume and the frequency range is wider. For general sound, the range and the frequency range and the volume is even larger. So next, let me introduce the taxonomy of sound. Sound can be categorized into audible sound, infrasound, and ultrasound. In this work, I will focus on the audible sound. For the infrasound, there are examples including elephants, whales, earthquakes, volcano. For ultrasound, the examples include bats, dolphins, teeth cleaning, and so on. For audible sound, it can be further categorized into nature sounds, for example, animals and environments, and speech, music, and artificial sounds. The artificial sounds examples include cars and cars brake. So audible sounds pattern recognition tasks, including 3 main tasks. The first one is audio tagging or audio classification, which is to predict the presence or absence of one or several audio events in an audio recording. The second task is called sound event detection, which is to detect the onset and offset time of the audio events in an audio recording. The third one is source separation, which aims to separate the waveform of the audio events in an audio recording. The third problem is also called a cocktail party problem, which is very difficult to solve. Here is an example of the 3 tasks. The first row shows the waveform of our audio recording. The second row shows the log mile spectrogram of an audio recording. And for audio tagging, we only need to predict the tags. For sound event detection, we can see there are many onset and offset times of sound events. For source separation, we need to separate their waveforms. And audio tagging is a very basic task in audio pattern recognition. And this work, we will focus on audio tagging. And large-scale weakly labeled dataset is available for audio tagging. And audio tagging is actually a very essential part for industry. And because we have many subtasks, those subtasks include acoustic scene classification, which can be further used for automatic speech recognition. The second is music tagging, which aims to classify audio into rock, classical, or other music genres. The third one is general audio tagging. The fourth is bird audio detection. And the fifth is audio set tagging. The sixth is speech emotion classification. There are also many other audio classification tasks that I didn't list here. But audio tagging is a very important task, and almost all the audio tagging systems can be shared the same system, while their training targets can be different. So first, let me introduce acoustic scene classification. Acoustic scene classification is a task to predict where an audio recording is recorded, such as airport or library. Here you can see 10 log mile spectrograms of 10 different acoustic scenes. For humans, it's very difficult to classify what sounds are they. But for machines, the accuracy can be up to 70%. In the following slides, I will introduce how we can build a classifier to classify those acoustic scenes. This slide introduces general audio tagging, which is a task to predict the audio tags in an audio recording, such as applause or clapping. So let's see the first row, the fourth column is about applause. The log mile spectrogram of applause is very similar to white noise. So from human, we can see that it's different from other patterns. So let's move on to the second row. The first column is a bicycle bell. So we can see there are harmony component in the log-mail spectrogram. So this is also different from other patterns. For the next task is more difficult because we are moving to audio set tagging, which is a task to tag real-world recordings extracted from YouTube. We can see there are many sound events in the first example. There are air horns, there are speech, and there are other sounds. Let me play the sound of the first spectrogram and see if you can find where the air horn happens. So we see the air horn happens between the second and the third second. Next, let me play the reverse beep. The reverse beep is very difficult to perceive. Well, we can see there's a line in the middle of the spectrogram. So this is a very important part to recognize the reverse beep. The third one is ambulance. So I played 3 demos here. And in this slide, it is more nature and it's more often happened in real world. And for industry, we are interested in how the sound recorded in real world can be recognized. Well, in previous slides, I introduced the sound events that are recorded in lab. So this can be different. We find that it's more complicated in the real world than the recordings recorded in the lab. So we often find that some systems perform almost 90% accuracy in the lab, almost drop 20% when we are moving the system into the real world. So maybe you are very interested in how we can build a system to recognize the sounds automatically. So the technique we used includes audio feature and a classifier. In previous, there are many audio features, including log mail spectrogram, mail frequency spectrogram coefficient, gamma tone feature, pitch, energy, zero cross ratio, and timbre. So in the past, we have a job occupation called feature engineer. So those engineers are designing features for audios every day. Well, after the years of the deep learning, those feature engineers, I believe many of them changed their job because we no longer need those jobs, because we can have spectrogram as input feature and only use the spectrogram as feature, and we build a classifier on top of that, we can achieve much higher accuracy than previous systems. So our conclusion is that for small data set, manually selected features are important. Well, for big data sets, use log mail spectrogram works pretty good. So for previous works, we can see there are many conventional systems, including hidden Markov model, spectral machine. I'm not planning to introduce all of them here. And let me move to the next slide, introducing the neural network-based methods. So our system is based on convolution neural network. We simply input the system with a log mail spectrogram. And after several convolution layers, we replace the fully connected layers with global pooling. This is because the duration of audio examples can be different. So with a global pooling, we can change the duration of the audio recordings into a fixed duration. And the convolution neural network can learn time frequency patterns of sound events in the log mail spectrum. For example, the pitch information. Audio tagging with neural networks has been deployed in the real applications, and there are some advanced systems, such as convolutional recurrent neural network. Because audio recordings are time series signals, there can be long time dependency in an audio recording. Convolution recurrent neural network applies recurrent layers after convolutional layers to capture long time dependency. Besides the log-mile spectrum as input feature, we can also build audio tagging systems from the waveforms. Audio signals are one-dimensional signal. They are research investigating to use waveforms as input instead of the log-mile spectrum. For example, the DINET applies a one-dimensional convolution neural network to build the system. There are also other systems, so I'm trying to briefly introduce some of them. Here, I introduce a crosstalk convolution neural network. The reason is that previous work mainly focused on individual tasks of audio tagging, and there is limited work investigating the same architecture across different audio tagging tasks. We apply convolution neural network with 5, 9, and 13 layers to all of 5 tasks in the DK's challenge. And we have some conclusions here. The performance of different tasks are different. We listed 5 tasks here. The first one is acoustic scene classification. The second one is audio tagging with noisy labels and minimal separation. The third one is sound event detection and sound event localization and detection. The fourth is sound event detection in domestic environments. The fifth is urban sound tagging. We find that the performance varies on different tasks. The 9-layer convolution neural network achieves good performance, and the 13 layers convolution neural network tends to overfit. Well, we have a question, is that how about with more data? So in industry, we have plenty of data. One example is the large-scale audio set tagging. The amount of data is important. Previous work focused on using datasets such as the DK's datasets containing only tens of hours of data for training. Recently, audio set with 5,800 hours audio data extracted from YouTube is released. Previous work focused on particular audio tagging problems with limited sound events, sound classes. We investigated the general audio tagging problem to detect a wide range of 527 kinds of sound classes in the world with a large amount of training data. Our goal is to train a state-of-the-art general audio tagging system of all kinds of sounds. And we want to provide pre-trained audio neural networks, which we call PANs, for a wide range of audio pattern recognition tasks. This is similar to pre-trained ImageNet for computer vision and BERT for natural language processing. We also want to investigate novel neural network architectures for large-scale audio set tagging. And we want to investigate lightweight systems that can be used for portable devices. So here I want to introduce a bit of audio set. Audio set is large-scale data set of manually annotated audio events. There are 2.1 million 10-second annotated videos, and there are 527 sound classes. There is an ontology organized in a tree structure, and the maximum depth is 6. Each audio clip contains multiple segments, and the average segment is 2.7. We find that each 10-second audio clip contains at least one tag. Over 800,000 audio clips contains one audio tag, and over 600,000 audio clips contains 2 audio tags. There are only a few audio clips contains over 7 audio tags. There are many challenges of audio set tagging. The first one is called weakly labeled. That is, audio clips are only labeled the presence of sound events, but not their onset and offset times. This is one difference between the academia data and the industry data. For academia data, we can strongly label a small amount of data, and it is possible. Well, for industry level data, we can't do the strong labels because we have maybe millions of data to need to be labeled. So we can only weakly label them. So this is a kind of difference between the industry data and academia data. Audio set is also highly unbalanced. This is because in real recordings or in the real world, some sound events such as speech usually happens. Well, for the sound events such as brushing teeth, that's very rare. So this is the audio set to be an unbalanced data set. Audio clips are noisy labeled, and there can be missing labels in the audio set. This reason is because the audio set labelers are not experts. They are from Epson Turk, and those are people who are not expert, and maybe just some people doing all kinds of labeling, or they don't have jobs and they are earning their jobs by labeling the data. So there can be noisy labeled data. And the last challenge is that the labels have an ontology of a tree structure. So this slide is a bit introduction of the audio set statistics. Audio set is highly unbalanced and provide a balanced subset with 20,000 audio clips and a full set with 2 million audio clips. Speech and music have 1 million audio clips. Several sound classes, such as toothbrush, only has hundreds of audio clips. This figure shows the magenta and the blue bars shows the number of training audio clips of the balanced subset and the full data set. So we can see the number of training clips of different sound classes are different. The audio set embedding features, instead of releasing the raw waveforms, audio set released the embedding features for 2 million audio clips extracted from VGE-ish network. And the VGE-ish is trained on YouTube 100 million. The embedding feature has a dimension of 128. So our very early research is on the embedding features. And we proposed some attention neural networks to tackle the weakly labeled problem because there are no information of onset and offset. So let's look into this equation. So the PX is a segment, the PX controls how much a segment to attend, and this is a detector, and the FX is a classifier controlling what sound event it belongs to. So our result is like we achieve and mean average precision of 0.361. And this is higher than the baseline of 0.314. So do we satisfied with this result? So we are not satisfied with this result because we think the embedding features provided by Google is not a very good representation. So our strategy is to download all the waveforms from YouTube, and we build a classifier by ourselves. So this slide shows some classification result. The curve shows the mean average precision sorted in descending order. Sound classes such as bagpipes have high mean average precision around 90%. Sound classes such as mouse has mean average precision around 10%. The performance is not always related with the number of training samples, and the performance is not always related with label quality. So this is a very interesting result. This means we don't need to collect a lot of training data in industry to build a good classifier for some sound events. So we can save a lot of people and money. We also tried to build the audio tagging systems with convolutional neural networks with 6, 10, and 14 layers, and we can go deeper with ResNet. We also build computational efficient systems with MobileNet because we want to move the systems into mobiles. And this is also an important part for the industry because for energy usage or the hardware on a mobile is very, very low. And we need to ensure that every system can be run on a mobile. And we set up several strategies to train the system. The first one is called data balancing. This is to solve the unbalanced data set problem. We balance each mini batch to contain approximately the same number of training samples from each sound class. The second one is called data augmentation. Some sound classes contains only 10th number of training samples. Data augmentation methods is applied to prevent systems from overfitting. Mixup linearly interpolate both input and target of two samples in the dataset to augment data. The input and target are denoted as X and Y. And here is the equation for the mix-up augmentation. Spectrogram augmentation randomly cut off time and frequency strips of a log-mel spectrum to augment data. So after we training on the waveform of YouTube videos, we achieve much higher accuracy than previous systems. So the first one shows the Google baseline achieves a mean average precision of 0.314, and the 14-layer convolutional neural network achieves a mean average precision of 0.431, and there is a large improvement compared with the baseline system. We find that the ResNet also slightly improves the mean average precision to 0.434. So we are very interested in the MobileNet's performance. MobileNet largely reduces the number of parameters and multi-adds, while it still achieves a mean average precision of 0.389. That does not decrease the performance much. So here are the most important conclusions of our system. The following figure shows the mean average precision of different sound classes over training iterations. The figure to the left shows the sound classes with the most training samples, and the figure to the right shows the sound classes with the least training samples. The audio set tagging performance does not have a strong correlation with the number of training samples. And we find that for some sound events, we only need to collect hundreds of the training samples, and we can achieve very good performance. Well, for some sound events, such as the inside small room, even we have 70,000 training samples, the mean average precision is still very low, like 20%. Next, we introduce the computation complexity of systems. The following figure shows the number of multi-adds versus the mean average precision of different audio set tagging systems. From left to right, the computational complexity increases. From bottom to the up, the mean average precision increases. After training the audio set, we can also transfer the system to other datasets. Our pre-trained audio pattern recognition system can be transferred to a wide range of audio pattern recognition tasks. In the following figure, the figure A shows the procedure of pre-training of a pen. The B shows transfer learning with pen as a feature extractor for other tasks. C shows the transfer learning with fine-tuning the pen. So we are interested in which one is the best for transfer learning. To begin with, we transfer our pens to the ESC50 dataset, which is an environmental sounds dataset consists of 50 sound events such as dog and rain. We find that the system fine-tuned on pens achieves an accuracy of 0.947, which is much higher than training from scratch. And we also find that fine-tuning all the weights perform better than only fine-tuning the last layer. The second dataset we tried is called Making Sense of Sound dataset. This is a task to predict an audio recording into one of 5 categories: nature, music, human and effects, and urban. The system fine-tuned and pan achieves an accuracy of 0.960, outperforming the previous state of art of 0.930. We also tried on the G10 dataset, which is a music genre classification dataset with 10 genres such as classical and country. The system fine-tuned on pan achieves an accuracy of 0.915, which is comparable to the state-of-the-art system. Finally, we tried on the recent audio-visual database of emotional speech and sound. So this is a human speech emotion dataset, including 8 emotions, such as happy and sad. The system fine-tuned on pans achieved an accuracy of 0.721, outperforming the previous state-of-the-art system. So those results shows that the system pre-trained on pans can be transferred to a wide range of applications. So this slide shows the demo of our sound event detection systems. The figure to the top left shows the probability of our predicted events.
Okay, no more. No more. Okay. Horse.
A high school girl's been murdered. Mr. Harrison's daughter is missing.
So you can see the sound events are detected correctly on the top left. Here is the conclusion of today's talk. So we introduced computation audition and its relation with computer vision. And I proposed the audio tagging with large-scale audio set dataset. And a wide range of convolution neural network systems are experimented. The proposed wavegram log-mail convolution neural network system achieves a state-of-the-art mean average precision of 0.439. The computational complexity of systems are investigated. The lightweight mobile nets achieve comparable performance of large convolution neural network systems. The pre-trained audio neural networks are transferred to other audio pattern recognition tasks and have achieved several state-of-the-art results. The pans can be used for real-time sound event detection. Source code are available. So here is the source code and demo. So I have, here is my talk for today. So I'm happy if there are any discussions or questions. Thank you.
Thank you very much, Chu Qiang. You gave us very detailed insights to your work about audio tagging. Any questions? We have half an hour to discuss. Please feel free to ask any questions in your man. If not, I have a question about, you mentioned that for small data sets, it would be necessary to choose some handcrafted features, and for large data sets, it is easy to train deep learning models from spectrograms or log mail spectrograms, whatever. In your experience, how do you define the small and big? Is there such as how many thousands data sets would be big in your experience?
Yeah, I believe this depends on the tasks. So for some tasks, maybe hundreds or thousands will be a roughly borderline that the handcraft features will outperform the automatically learned features. So I believe there is not an accurate how many hours or how many minutes we have, but I thought it will be maybe 5 hours or 10 hours. So well, audio set is 5,000 hours, so it's already very much larger than small data sets. So we don't have this problem. But yeah, for a startup company, if they have for example, 5 hours or 10,000 hours of data, I think they should use deep learning.
Okay, great. I would like to follow a question because in our domain of speech pathology or any healthcare domains, because it's very difficult or challenging to collect such a big scale data. It's not like the audio tagging audio set. So normally we often have only less than 10 hours data. In the whole data set, there might be only less than 1,000 audio samples. I'm curious if your models, your pre-trained models are also released, and do you have any insights for us to use transfer learning to transfer your model to some other speech pathology tasks?
Yes, so the motivation of this research is to build a general audio tagging system that can be applied to some sound events. For example, if you have only 5 minutes of sound, so how can you build a large scale system using only 5 minutes? So our solution is we have a pre-trained model, and you can fine tune this model with your 5-minute data. So this is a way how we can keep the knowledge from a lot of domain knowledge. And also we have your new data, and we can fine tune this new data to the new task. Well, we still have a new question. So the domain knowledge of medical and the domain knowledge of general sound can be very different. So this can limit the performance of audio tagging system in medicine or in your task. So I think maybe for future or the proper way is to, if you have a very large scale speaker data or the medicine speech data, and how can you build a general model using this large amount of data and apply your general model to your task, even if you have only 1 minute of data or 5 minutes of data. So you can still fine tune your model on the pre-trained model. So I believe this can be very helpful.
Thanks. Yeah, please.
Hi, thank you for that excellent talk. Really made me think. I had one question, and it's probably related to the previous one. So if you have a long piece of audio in which interesting events are happening, do you think that there's a way to select parts of that audio and say find sounds like this? Okay, so you've got this long, maybe 1 hour or 2 hour recording, and this this selection, of course, will map to some class that you've got, but that's not that interesting for me. I'd like to say, okay, can you find sounds like this in this recording? So again, it's almost like training it on the fly with literally a segment that's few seconds long. I mean, any thoughts on how this could work or any suggestions?
So this is another research topic, which is called you can call it cover sound identification.
Sorry?
Cover sound identification. Or you can call it query by singing or humming. So the idea can be similar. So you have an audio and you want to retrieve something very similar to that. So the way is to calculate its embedding and trying to find the embedding in the very long 1 hour audio, which embedding is the most closed one. So that's one way. And yeah, so I think there are many research on this, especially in, we call that people re-identification. So you want to find the people who, a large amount of people who is the real one in the image you want to retrieve.
Mm-hmm. I'm thinking of sort of more general purpose problem, and I get what you're saying, where you extract the embedding and then you look across. But is there any way of leveraging these pre-trained models for it that you've got, and kind of using that to help you do the search? So, say you showed some nice beeps in the beginning, or you showed some tones, or I want to see if I can use that as a model to look across. So pretty much, exactly that, or very similar to that. I get the singing analogy, but I'm not sure that's quite the same. Is it? And maybe this is a common topic, so excuse me if I don't know.
Yeah. Well, the embedding is quite important if you want to any kind of search. So yeah, well, the searching mechanisms or searching algorithms can be a different topic of the recognition. So I think this can be different.
Okay, fair enough.
Okay, thanks.
Thank you.
I saw in our chat, there's a question from Katin. She said her internet connection is currently very bad, so I will help her to ask her question. She asked, do you have any experiences with automatic recognition of baby or child speech? If yes, how good does it work?
Have experience with automatic recognition of baby or child speech? Yes. So for the audio tagging, this data set includes baby or child speech. So we could detect whether there is a baby speech or there is a child speech in the data set. So it is one of 527 sound classes. So it is possible. So how does it work? The easiest way is to take the, for example, the pre-trained neural network, and we have 527 predictions. You just take the head of child or speech, then you have the result.
Sounds interesting, because we have a data set in interspeech compare challenge previously. There's a baby sound database to predict what's the requirements of the baby from their cries. Yeah, if they're hungry or something else, that would be interesting to maybe use these two data sets together to train. How do you think?
Yeah, we can use the two data sets together to train.
Okay, any more questions?
Yeah, I see one question. So the question is about there can be multiple tags, how to solve this problem during training process. So for if we have single tag, so it's a called classification problem. We use categorical cross entropy loss function to train. For multiple tags, we call that the tagging problem, and we use binary cross entropy on every single sound class to train. So this is the answer.
Yeah. Okay, I'd like to follow another question from myself. usually in industry, you said that most audio data are weakly labeled because it is large scale, so there won't be enough human annotators to label the data in details. So if in industry you want to apply the audio tagging to smart devices such as mobiles or any more devices for real-time audio tagging. So how long time, for example, if I will do this, I will put small audio segments for training deep learning models. So do you have any similar experiences on developing real-time audio tagging applications? And if you have, how long time does each audio sample should have? 1 second, 2 seconds, or longer?
Yeah, so I think there are two questions for building the real-time applications. The first one is, how can we make the prediction system casual? So we can't look future to make the prediction. Well, we could use the history informations. So that's possible. So we not only use the current, let's say 1 second, we can also use the past 10 seconds for predicting the current speech or the current prediction. Well, for the second problem is, how can we build a system that's small enough for real-time applications? Because we want the prediction to be on time to stream. So that's a kind of things we need to make the model small. So yeah, there are two questions.
Makes sense. Yeah, very interesting. You also mentioned you used CRNN because CNN can extract special audio information, and the RNN can extract the sequential information from audio waves. I know in some recent studies, researchers show that a transformer performed better might be than RNN. Do you have some more experiences on this? And do you have any more suggestions?
I think transformer can replace recurrent neural network. So it is one research topic to do in future. Because RNN is you need to calculate one by one, but transformer can calculate in parallel. So there are many advantages. And you can also see transformer types being applied to many audio related applications.
But transformer doesn't consider the sequential information. It calculates the whole sequences in the meantime. So will it increase the computation complexity?
Could be. Well, there are some engineering things we need to fix if we want to use a transformer or recurrent neural networks. And there are also many people in the company doing this kind of optimization. So there are some things need to be fixed.
Okay, thanks. Any more questions?
Yeah, I have questions. Sorry. You just mentioned that when you predict some things, you will use the history and I mean past states and audio waves to predict the future. So I want to know how will you to assign the weights between the past and the now, you know? Can you? Yeah.
Yeah. So I thought the question is about how can we use history information
Yeah.
And yeah, so for a recurrent neural network, so if you have the prediction of the previous one, and when you want to predict the current one, you can take the state of the previous step to predict the current step. And this is possible. So I'm not sure if I answered this question.
Okay, thank you.
Very interesting. Any more questions? Okay, if there's no question, I will follow one more question about your experience, difference in industry and academia, because Qiu Qiang is also a young researcher. You graduated 2 years ago. So how do you think, what's the potential benefits of cooperations between industry and academia?
I think there is more connections between industry and academia in recent years, especially for computer science. And so different from other subjects that the research are mainly done in the lab. So we can see there are many research done in the industry as well. So I thought the industry people should keep an eye on the academia, what's happening, what's the most recent research. And the people from the academia should also look into the good ways or good manners of coding and everything from the industry. And you can see in the industry, there are more people working together. For example, 10 people or even 20 people working on the same project and even working on the same repo. So there are many things we need to fix we need to be careful when cooperating together, especially when writing code. Well, for the academia, most of the time we are writing code ourselves. So this can be different.
Exactly.
Hello, I have a question. Thanks for your research. There is my question. There is overlap in some tag classification, and the tags may not be appropriate. So how do you solve it? It's like a weak text, not a strong labeled data set. Do you meet this? Have you met this problem?
Can you give an example of the thing you just said?
Thank you.
Oh, just give a brief introduction. So maybe the question is about there are some overlap between weak labels and strong labels. So it's a multi-tag problem. So we allow there are some overlap in the weak labels, and we didn't use strong labels for training. So the overlap in strong labels is not a problem for us.
Okay, thank you.
Okay, thank you.
Thanks. Any questions?
Yeah, hello. So I have a question regarding to the one slide that very previously. So I saw you when you mentioned the application of the audio, there is one like home and health, I think.
Yes.
Yeah. So I saw you mentioned like we can detect the fall down for some old people. I'm really curious about how do you detect the person fall down just according to the audio, based on the audio.
Yeah. So the first thing is that we need to collect some of the falling down sound. For example, we can collect 50 or 100 demos, 100 examples of falling down. Then we can use these examples to fine-tune our pre-trained audio tagging systems. So that's a kind of adding one more head onto the 527 head. So we have 528. So the extra one head is about falling down. So then in the inference, we can predict the falling down probability using the fine-tuned system.
Okay, but like, is that enough for you to have just 100 example for the falling down? Because from my understanding, like there are really different ways to fall down.
Yes.
Yeah, different like angles, different place, or different floor materials. So we will have like really different sound for falling down.
Yeah, so if you are training a system from scratch, 100 is not enough. Well, if you have already have many prior knowledge of what a sound is about. So just give you an example. If you just hear falling down sound for 10 examples, you will know what's falling down. So for a computer, our after fine-tuning, we have knowledge of 2 million audio clips. So this is our prior knowledge. So after you fine-tuning on 100 examples, so the machine will know what's falling down.
Okay. Yeah, I have a following question. Like in your field, do you have something like similar to, for example, in the ASR system, we have like speaker variation, like speaker variability. So I think when you do the audio tagging, do you have some like sound variability? How do you solve that?
In building these audio tagging systems, we didn't tackle different speakers. So if we want to distinguish different speakers, you may need to use some data sets that includes thousands of different speakers to train speaker tagging systems for fine-tuning on other tasks.
Okay, but I mean, not only speaker. For example, falling down will have like falling down sound variability, or you have like other music variability. Have you like thought about how to tackle that variabilities?
Oh, so this is a good question. So this is about the granularity of your classification systems. So for our audio tagging systems, we have a very rough granularity. So after music, we didn't distinguish if it is this genre or that genre. But if you want to have more granularity, you want to distinguish if this is pop music and this is from another singer and this is from another singer. So you need to retrain the system or collect some related data set to do this. But it is possible. So that means we have more granularity when you train the system.
Granularity. Could you please type that word?
I can type in the group.
Okay. Yeah, thank you for your answer.
Yeah, thanks.
May I ask a following up question?
Yes, sure.
How about if you have two tagging that have very similar sound, for example, the falling down and something dropping on the floor, then this sounds very similar, right?
Yes, this sounds very similar. And this can be difficult to classify. So if you have something dropping down on the floor or you have a falling grandpa, so our system may give very similar prediction. So to solve this problem, maybe you will need to collect some pairs of data. For example, somebody is really falling down and something is falling down. You treat the human falling down as positive examples and things falling down as negative examples to fine-tune the system.
Okay, thank you.
Thank you.
Okay, very interesting discussions. Anyone has any questions? if there's no question, we thanks a lot to Chu Tian giving a very interesting talk. Chu Tian also gave his email address in our chat. You could feel free to contact Chu Tian, I think, right? If you want to have more discussions with him. Okay, so we would like to end our talk of Chu Tian in this morning. Thank you very much, Chu Tian. And our next session in this afternoon will start from 2:00 p.m. CET time. Looking forward to see you all in this afternoon.
Okay, thank you, everybody, and bye.
Thank you. Bye.
Thank you. Bye.